Hello, everyone, and welcome to DMC's webinar series. My name is Lexi, and I will be your host. In today's session, we'll be covering crimp quality and validation. We'll talk about best practices, the problems and solutions, design validation, and how DMC maintains the highest standard of quality. To talk about this topic, I am joined by John and Kirk. Please tell us a little bit about yourselves.
Yeah, my name is Kirk Coons. I'm the principal engineer here at DMC. Been here for about 26 years in the design engineering department, designing tools. So a lot of experiencing a lot of things in the crimp tool industry.
And I'm John Connor. I'm the operations manager here, working in a couple different departments, and I've been with DMC for about 6 years now.
Awesome. Well, thank you guys so much for being here with us today. For our attendees, if you have any questions at any point during our webinar, feel free to drop them in the Q&A tab that's at the bottom of your screen. We'll either answer them as we go throughout the webinar today or during a dedicated Q&A session at the end. Okay, well, Kirk, let's get started by asking the question, why is crimp quality and validation important?
Yeah, so the tools that we make, they're used in high reliability industries. Yeah. So, you're talking aerospace, defense, military defense, commercial air travel type things, subsea things, outer space. Even, we dabble in a little bit of medical stuff too.
Right.
So you'd be in high reliability industries, they're places where the crimp connection, it can't fail, right? So because there's catastrophic problems if it fails
Right.
in there. So yeah, it's really why you have to go through a lot of standard testing and validation to ensure that it is a good crimp.
Yeah, and that brings me to my next point. What would the goal of validation be, and generally, how would it be achieved?
Yeah, so the first goal in this and as in a lot of things is safety, right? So again, because you can't have something fail in the field because things are flying in the air, they're way underwater, and bad problems are bad things. So yeah, safety is the first issue. Generally coming across there, and then compliance is the next one. There's a lot of history over the years of standards that have been set of what is a good crimp tool and what is a good crimp connection, and that so it's compliance to those standards that exist already,
Right.
And then also the repeatability of the crimp. Because a lot of these tools, they get used in thousands and thousands of iterations over and over, and you want that first crimp and that 200,000th crimp to be the exact same.
Right. Right. And when trying to design a good crimp, how do you get there?
Well, there's a series of structured testing that you go through that by the time you've gone through all those tests, it's, you can be rest assured that you have a good crimp, that it's going to perform how it's supposed to perform in there. And then, and it's also adherence to those compliance standards that are out there, because there's a lot of history over the years that, like I said, as to what is good. So yeah, it's a lot of that, structured testing and then compliance to the existing, regulations and standards.
Right. And can you walk us through the exact pathway to get to the end goal, the solution?
Yeah. So a lot of times we get presented with a problem. It's either something's not working or somebody's come up with a new application. They got a new contact, a new connector, something like that. We'll then usually refer to the regulations. Those existing standards that are already there to see whether it falls under one of those regulations or it's closely related or something to get some guidance, some design guidance on where you would go. And at that point, we enter into a design iteration kind of loop, right? So we have the problem, some guidance from regulations, potentially from the customer as well. And then you go and we're going to design something, try and validate it, iterate if we need to, till ultimately you get a solution at the end.
Right. And can you walk us through the validation solutions? What are they? How many are there?
Yeah, so there's essentially 5 standard validating tests that we're going to cover in a little bit more detail here coming up. But it's you start with visual, you crimp something, you can look at it and see whether it's been damaged, cracked, or whatever.
Right.
And there could be some potential problems you can just see with your eye. And then you're going to move on to mechanical tensile testing, which is, a mechanical physical separation kind of a process there. And then you might cross-section your connection to take a look on the inside of what it looks like. And then there's some electrical tests that can be done, millivolt drop testing to check for voltage loss in the connection, and then dielectric strength testing for insulated terminals.
Awesome. And John, can you start with laying out the problems that we see in the industry today?
Yeah, sure. So today, your common problems will categorize into five main buckets. You're going to have physical damage, mechanical failure, compaction problems, a voltage drop, and arcing.
Right. And how can you tell that a crimp might be damaged physically?
Sure, physical damage is really your first indicator that you might have had a process or some sort of tooling breakdown. You're going to see probably about five main failure modes there. You're going to have cracking, breaking, loose strands. You might have excessive deformation of the contact or around the wire barrel, and then of course crimp location. It's really important to stress too that these are more than just cosmetic red flags. They're really a signal of some sort of underlying process or tooling problem that you have going on.
Great. Okay. So we got physical damage covered. Now let's move on to mechanical failure. Kirk, what is it and how is it caused?
Well, yeah, mechanical failure is when the what you've applied, you've put your contact onto the wire
Hmm.
and it has separated from the wire, right?
Right.
So that failure would be, something has caused it to separate your contact and wire that you would crimp together.
Okay. And how can you be sure that your crimp won't fall victim to the separation and over or under crimping?
That's where we move into tensile testing. Is the solution for that. So you essentially apply a load to the crimped connection, grabbing a hold of the uh, crimped contact and then the wire itself on the other side, and you attempt to separate it and measure the force that it takes to do that, and then look at the end condition of what the failure mode was as well. And those can be, they can be caused by over crimping and under crimping. So
Mhm.
under crimping kind of logically makes sense. If you don't crimp it enough, it's going to pull out real easily. But
Right.
actually, over crimping can also be a big problem too, as
Right.
well.
And for tensile testing, does DMC make any tools for this?
Yeah, we have a whole line of tensile testing tools. We have handheld versions that are manually operated by the operator. And then there's also benchtop manual versions that the operator then pulls a handle to activate the crimp or activate the tensile.
Right.
And then we also have our motorized version, which is our MPT-250C model. Um, and we're going to run through, and also another thing is we have a couple different kinds of testing. Sometimes you do destructive testing, which is what we're going to demo here, where you're going to pull it until essentially it fails, it comes apart. But
Right.
you can also do non-destructive testing where you're essentially doing kind of proof loading, where you might load it up to some value underneath of the minimum requirement, hold it for a certain amount of time, and then move on. So moving on to our demo over here. When you come to we're going to do a destructive test on a contact. From the main menu there, you can see that you can select your type of test, which is going to be a pull to fail. You can set the pull rate and then also the units. And once you've made all those selections, you can press that green test button in there to move to the testing mode. And at that point, you would load up your contact. And you're going to load the contact in the non-moving grip, grabbing the mating end of it so that we're not pinching the crimped connection. And then we're going to wrap the wire and clamp that down on the moving side. And sometimes when you're clamping that other side, the wheel may have moved off of the home position. So you want to hit the home button. And at that point, you can press start. And you'll get a constant reading on the right-hand side there in the green numbers. And then on the left-hand side, once we eventually get a failure, you'll get a minimum, or I'm sorry, a peak force break inside of there. And what we're looking here, depending on the size of the wire, there's a certain minimum force that's required, and you'll want that peak force to be somewhere above that minimum value.
You guys here one more time. We had a little technical difficulty there, so it wasn't live. So, John, would you mind giving them another demo of that?
Yeah, so we rehome that wheel back to the home position. So we're back at our start, and then we'll load back up. And if reneeded, we'll home again and then press the start. And again, we'll get constant readings on the side and then a peak force value when the separation actually occurs. And all of this information can be, if there's data logging inside of this motorized unit as well, that can output the recordings of all these tests being done for future use to keep the data for validation reasons.
Okay, while that tensile tester goes, we're going to move on to our next problem, which is compaction. So, John, can you explain the issues that you see today with this?
Sure. So this really falls into two main things. You can have under compaction or over compaction. When you have under compaction, it's usually indicative that you didn't have enough force potentially applied through the tool onto the contact.
Right.
And if it's over compressed, you may have had the wrong selector setting where you push too far in. That can cause other problems as well. Both of those can lead to different defects, right? The tensile test that we just performed, typically you'll find it there first.
Right. And what kind of testing can you do for this besides tensile testing to make sure you don't have a compaction problem?
Sure. So compaction, the most common way to do that is to perform a cross section. So doing a cross section test, what you're going to be doing is taking a specialized setup. Typically it's a fine saw, and then you'll be sectioning right across the actual crimp joint itself. And then you'll be polishing that crimp joint with an abrasive wheel or an electrochemical solution, and then taking a micrograph of that cross section. Once you do that micrograph, you'll be looking to see if all the strands are present, if they all have deformation, making sure that the wire barrel wall is uniformly deformed, and making sure that the geometry itself is working the way that you want it to.
Great. And would you mind walking us through some examples of cross-sectioning failures?
Of course. So when you're doing that cross section, you can really get a good idea of what's going on within that termination itself. On F crimps, some common failure modes is you can get stranded conductor. You can see in the top left corner of this picture where you have a few strands that are stuck in the wings of that F crimp there. If you have under compression as well, you could get loose strands sticking out of the top of an open wire barrel. You also get to validate your geometry as well. In the top right picture there, you get to see where potentially the wrong tool was used, giving you an awkward shape, which would lead to poor conductivity, right? Increased grip resistance, as well as poor mechanical strength. On closed wire barrels, you'll be able to get a really good idea to make sure everything is uniform, that the indenters or the die halves came together correctly. You're looking to make sure that all of your strands are deformed, indicating that you got that good cold weld, which is really the heart of a good termination there.
Awesome. Well, let's move on to our next problem, voltage drop. So, Kurt, can you explain to our viewers what this is and how it can negatively affect a connection?
Yeah. So voltage drop, every time you connect two pieces together, right, you're connecting that contact onto the wire. There's a certain amount of voltage that's lost in that crimped connection.
Right.
It's not 100% perfect. So what you're basically looking for is to see how much voltage is lost. You're measuring that amount. Because again, back to those industry standards, there's been a predetermined amount of allowable voltage loss in a crimped connection across the crimp connection.
Right. And how can you validate that you don't have a millivolt drop issue?
There's a millivolt drop test, right? So what that is, essentially you have a crimped wire connection. It's set between 2 points. You can see on the right-hand side there, the crimped connection is set between those two posts, and there's the meter probe goes on a predetermined, on either side of your crimped connection at a predetermined distance. And then the unit on the right there sends a certain amount of current, depending on your wire size, through the system, and you physically measure the millivolt loss across those 2 points in there. And that current range is dictated on that. You can see on the chart on the right, depending on your wire size, you put a certain number of amps through the system. And then there's also in that same chart dictated how much voltage you can actually lose.
Right. Yeah, that's a good resource. So John, arcing is our next problem. Can you explain what this is and the complications that could happen?
Sure. So arcing occurs when you have any sort of electric discharge between an electrified feature and maybe something else on an aircraft or a structural member on whatever it is that you're working with there. Usually that'll happen when you have some sort of insulation breakdown or you have improper spacing across different connecting members.
Right. And that sounds dangerous. So how can someone test to know if they have those issues?
Sure. So this sort of test that we're going to talk about next is called dielectric strength testing. It's usually done on an insulated terminal or some sort of other termination where you might have to put an insulation sleeve. We'll test that first, By taking a terminal, doing the termination, you're going to do your visual check to make sure that you don't have any torn insulation or anything like that. And then we have a video to kind of walk us through the process next. So here at DMC, or anyone, what you're going to do is make sure that you're covering all the bare metal for whatever you're trying to test. You're going to cover it with beeswax or some other resin or something like that that's going to prevent any sort of leakage. Make sure that that's completely covered. And then the next thing that you're going to do is submerge that into a salt solution. From there, you're going to hook up your test leads. One goes into the solution itself, one onto your test article, and then you're going to put that underneath high potential, right? So very high voltage. And what you're going to be looking for is to see if there's any sort of current loss across that. If you don't have any current loss, then you have a good, solid termination. But if you do have something like a tear or a rip, you'll find some a current leak across that.
Right. So definitely a necessary test. So now we have the 5 common industry problems and solutions established. I think it's now important to consider the regulations and specifications that define a good or bad crimp. So Kirk, can you walk us through that?
Yeah. So, as we've been talking about, there's a lot of industry standards that have been established over the years for what is good.
Right.
And so there's a lot of them out there. There's things like IPC 620, which relates to crimping and completely, crimping, soldering, wire harness build. It covers a lot of different things in that. Yeah, it's a lot of workmanship type standards. What looks good, what's properly done, what isn't, and a lot of good examples of, this is good, this is bad with pictures and everything.
Right.
AS 22520 is a crimp tool standard. That's one of our bread and butter type ones where a lot of tools are listed in there because that's what we make as crimp tools, right? 7928 is a terminal lug type of a spec around the actual lugs and terminals themselves for those larger insulated, uninsulated type terminals and lugs. AS 39 and 29, that one relates to mill standard circular mill kind of contacts. 5259 is another large gauge terminal lug, and that one covers tools and dies for large gauge terminal crimping. And then your AS 50881, that's a kind of a practices manual where you get through it, and it covers everything from selection and design and installation, like what's the proper way to do it. It's a military one that covers all those kind of things.
Right. And John, how does DMC support these requirements?
Sure. Since 1949, Daniels Manufacturing has been really founded on reliability and precision. So that translates to our crimp tools as well. We are heavily involved in a lot of the standards development organizations that work to build and maintain these standards that Kirk talked about, as well as new ones.
Right, that's awesome. Okay, well, thank you both. To sum everything up, we learned that crimp quality is critical to ensuring reliable and safe electrical connections. From common failure points to validation methods and industry specifications, there are several factors to consider when selecting proper tooling. For anyone looking for any additional resources or guidance, do we offer any type of engineering support, Kirk?
Yeah. So, we offer support in new tool design as well. That's our main focus, but we also offer testing services as well. So any of these type testing that can be done, even if it's just visual, submitting samples, we can take a look at them kind of thing. But we offer tensile testing, the dielectric millivolt drop, all of those testing, the crimp cross-sectioning. We offer it as a service as well.
Awesome. Yeah. Well, in addition to the support that our engineering team offers, we also have regional support provided by our dedicated national account executives. We also have distributors across the globe, as well as our subsidiary company, DMC Europe. So feel free to contact any of those places to find support. You can also visit our website for resources, including literature and videos. Check out the link in the resources tab for links to all of those items. And then, of course, our awesome customer service team can assist with any questions. And speaking of questions, we've had a few that came in. We'll start answering them now, but if you have any additional questions, we'll open up the floor. So drop those in the Q&A tab at the bottom of your screen. So let's get started with the first question. This is from Chris. He asks, why does nickel-plated wire have significantly higher millivolt drop than silver or tin-plated wire?
Yeah, that's a really good question. So nickel-plated wire is becoming more common, especially in high-temperature applications. The nickel plating itself has a different resistivity than the gold or silver or some other plating materials that you see out there.
Right.
So whenever you're working with that, you'll typically find, because one, it's harder, right? So you'll have a lower tensile value as well. And then it also changes your millivolt drop because of that different resistivity, characteristic resistivity.
Right. Awesome. The next question is from Andy. He says, hello, what are the most common root causes behind crimp failures that you see in the field?
Usually comes down to the user. It's not to blame the person, but it comes down to the wrong application. You
Right.
either had the wrong tool for the crimp to be done, or it was on the wrong setting, or maybe they had the wrong positioner on there. So it's a lot of making sure you have everything correct.
Right.
You're using the right stuff.
Yeah, and something really helpful for that I think we should mention today is our tool selection search available on the DMC website. It's right at the top of the browser. You click it and you can find whatever tooling you need for your component that you're using or connector. Very helpful, and a lot of customers have had success using that. So definitely a resource to try out. Okay, another question is, what is the recommended ideal compression ratio?
Sure. So compression ratio relative to compaction really kind of depends on what standard you're working toward. General rule of thumb is that 70 to 80% range. That usually comes out of an open wire barrel design guide. As you get into closed wire barrels, like a machine contact, that can vary. You're really looking for more qualitative type acceptance criteria to make sure that you have deformation of all of the strands, minimizing your voids, and making sure that you've got the right geometry and everything looks symmetric.
Right, makes sense. Okay, another question from Ricardo. He says, is compaction used to determine acceptable crimping of heavy gauge cables? If so, what are the ranges of acceptance?
Sure. So that's another one. Again, it depends on what you're working toward. If you're working toward an industry standard, like an automotive standard, like used car 21, there are very specific requirements relative to that.
Right.
Outside of that, it could be a process specification or some sort of engineering requirement that may be dictated there. Again, you're looking at those qualitative type characteristics to ensure that you've got the proper termination.
Makes sense. Another question from Stephen. Does DMC utilize USC AR 21-4 crimping spec?
Sure. So that's not, so for us, we typically work around the military specifications, right? So we live within 50881 is kind of the granddaddy there.
Right.
And then the 22520 is the performance specifications for the tools. That all meets within the AS 39029 and 7928 specs for the contacts or the terminals themselves. However, being that we do offer a very wide range of engineering services, we're very familiar with that. We do a lot of projects with that as well. So if anybody ever has a question about any of this stuff that either isn't fully answered today, or they've got a specific application that they need help with, they can always email into us or call us, and the engineering team is happy to support any sort of testing that they may need.
Absolutely. Okay, we have a follow-up question from Andy. He said, thank you, Kirk. In that case, how often should validation testing be performed in a production environment?
If you're talking about validating the crimp or validating the tool, either one, well, really both. A lot of times it's generally set by the end user as far as what they deem acceptable, but a lot of times it's before the thing's used. Right, you got a job, you're supposed to crimp, however many terminals onto this one harness or whatever. They're going to validate that tool beforehand. They're going to validate that they have the right tool, they have the right position, or the tool's on the right setting. And you're usually going to gauge that tool as well to make sure that it is closing to the proper amount, or the die is closing to the proper amount, either one,
right,
before any work is done. That way, because they know it's a validated solution, so you verify that you're using the correct solution first.
Awesome. Okay, a question from Chris. What standard dictates the distance away from the contact for the MV drop test?
It's in the AS 22520 spec. That one there, I believe it's half an inch on either, as far as the distance between the probes with the crimped connection in the middle.
Perfect. Another question, what is the purpose of bell mouth on stamped and formed crimps?
Sure. So the bell mouth really gives you a good edge break off of that termination. If you have your tooling or your die coming down and it pinches with a hard edge, you put a stressorizer there. So that can allow for that termination, or that conductor to break easily under improper loading or even just normal operational loading conditions.
Perfect. Another question, can multiple test methods be combined for better validation, or should they?
Yeah.
Yeah.
Yeah. I mean, you start with visual, you can see the
Mhm.
stuff, and Tensil's pretty standard. But when you get into mechanical testing, that crimp cross section, it can tell you a lot. You can, like John was saying, you can verify that all the strands are in there. They all got inserted into the wire barrel for the crimp. You can see any internal cracking that might be happening inside of the crimped connection that you can't see on the outside, small ones.
Right.
You can look for all the voids inside there to make sure they're all either fully gone or mostly gone, depending on the spec. You may be allowed a little bit of them out. Um, so yeah, I mean that's the next level of literally cutting in half and looking and seeing what's inside there.
Right.
And then obviously the electrical testing, depending on whether you're doing insulated, uninsulated, that kind of thing. That's that next level of, is it a good electrical connection above and beyond just a mechanical connection?
Right.
Mm-hmm.
Okay, another question. From your perspective, can a crimp meet a pull test but still contain voids acceptable?
That's a really good question, and it really depends on the standard in the application, right? So the cross section is a little controversial when it comes to the military world because that's not necessarily something that is a standard thing. But when you find failures because of thermal aging testing, contact resistance, or something like that, that cross section can really tell you a lot when you get into it. So
Right.
typically not something that you're going to do on the production environment or on the floor out there to verify at the beginning of a shift or something like that. That's really done at the engineering level or the tool application development level, like what we would be doing here.
Right.
Usually then you just be doing some sort of tensile test to make sure that everything is working correctly.
Yeah. If you have that engineered solution already
Mm-hmm.
that's already been vetted out on our end, that then you can take and gauge the tool.
Right.
And you can then do a validated pull test and know that I'm using the right thing. It's been vetted out that the cross section is going to be acceptable.
Yeah.
Right.
Yeah, that really gets to a lot of different things as well. And also going back to the application a little bit, something with a lot of temperature cycling or high thermal gradients, we'll say, through the use of that contact. The more that you compress that, the better off it might be. It also helps with your thermal aging from building up any sort of oxidation or anything like that as well. So voids aren't bad, but it depends on how many are you allowed to have, and that's very application dependent.
Right. Makes sense. Another question, what is the best component to crimp and crimp style? Kind of goes hand in hand with the previous question. It's kind of up to the user.
It does depend on the application too, right? I mean, there's terminals and lugs, commercial type things, and then you got your mill arrow circular kind of stuff there. With those kind, the foreign dent crimp is the way to go on those. With your terminal lugs, it's going to be a die type crimp.
Right.
So it really varies depending on what the application actually is, as far as like. Yeah, I would suppose the component is probably determined by the application, and then the component would then determine what is the best tool to use.
Right.
Makes
Yeah,
sense.
the termination itself, there are some things you definitely want to watch out for, like using an indent tool on a terminal, especially if it has a split seam on the wire barrel. So your tooling really gets driven by that component selection that you have. So there is no one best. It really depends on what you're trying to achieve.
Right. Okay, another question. What are the symptoms of poor crimping existing or voids being present within a connection point?
Sure, we touched on that a little bit before. So if you've got a lot of thermal cycling, what can happen, or if you have two different types of metals, right? This is very common in aluminum. You can build oxidation, and that'll end up causing increased heat, right? And then your termination will fail. You'll get some sort of oxidation inside their oxide layer. If you've got too much voids, that's kind of a visual indicator that you might have a poor mechanical connection. So your wire may pull out just through handling or while it's in use on whatever that application is.
Right. Okay, another one. Does the choice of crimp type or shape change for a terminal based on how fine the stranding of a cable is?
It can, right? So super fine stranding wire typically requires a little bit more of what would be over compression for normal stranding, right? So you need to really press hard to get that deformation on all of your strands in order to get a good termination there. So a lot of high flex cable that's becoming more popular, especially within the eVTOL and the high voltage world. You want to maintain those bend radii so that you can easily put your aircraft together or whatever it is that you're working with.
Mhm.
So things get a little bit different there, and we work through different solutions where you might have a combination of different termination styles so that you can achieve that compression that you need without also overcomplicating your process.
Right.
Mhm.
Awesome. Okay, let's see. We've got some more questions coming in. Someone asked how much stripped wire should remain exposed behind the wire barrel on M39029 contacts.
That's in the, I think it's the AS22520, probably in the 3929 spec as well. But it's usually, it's flush to the end to, I believe it's about as much as 30 thou is the most you're allowed to have back there as far as that gap between your crimped before your insulation starts.
Mhm.
Because you
Sounds
don't want
like-
insulation down in the barrel and you don't want it way far away from the barrel where you got a bunch of exposed wire. So it's essentially flushed. I think the number is 30 thousandths if I recall correctly.
Right.
Yeah.
Sounds like to always refer to the spec.
Yeah,
Get information.
The AS spec
Yeah.
would certainly tell you for sure.
Awesome.
Probably an IPC 620 too.
It is.
Another question, does the choice of crimp type or shape change for a terminal based on how fine? Oh, we've asked that one already. Okay. What?
Answer is yes.
Yes. Yes, again, for a second time.
Help would be happy to help you with that.
Yeah. What resources would you recommend for teams looking to improve their process? We kind of talked about a little engineering support that we have, our tool selection search, or any additional resources you guys can think of for our customers.
I go first and foremost to our NAEs, right?
Mhm.
They're all over the country. Frankly, we got people all over the world that are experts in not just tooling and application, but process too.
Right.
So if you ever have any question, how can I make this process work a little bit better? They're the first stop.
Absolutely. Any recommendations for a double crimp application best practices?
Yeah, so typically you'll see that on something maybe more in the commercial world, like a UL or something like that, where you may have to do multiple hex type terminations. Depending on what you're trying to work with, of course, you may need some sort of assembly jig or locators and things like that on dies. That's where custom derivative tooling may be helpful for something like that. Again, very application dependent.
Yeah. A lot
But-
of that, sorry. A lot of that comes from the terminal manufacturer too.
It does.
They'll tell you exactly, that you crimp with this tool,
Mhm.
and then they'll say, it takes one crimp, two crimps, sometimes three crimps
Mhm.
along the length. They have like long tube type barrels on them.
Okay. Another question, what is the recommended pull rate for tinsel testing?
In the AS22520, it's 2 inches per minute is the sort of standard. We have come across other stands where people want it pulled faster. The motorized unit that we have does 1 to 10 inches per minute. So you can do anywhere from 1 inch increments. So 1, 2,
Right.
3 up to 10. The standard that we usually work by is the 2 inch per minute.
This kind of goes hand in hand with that, but is there a way to test the pull strength without being destructive?
Yeah, our motorized tester does that really well. It's ideal for that because it has there's a computer inside of it that's telling it how much to pull. So yeah, that one, you pull it up to some load underneath, it'll hold it for a certain amount of time, whatever you put into the unit, and then it releases after that.
Right.
So you're doing non-destructive testing there.
Awesome. Are there any testing standards for the shield termination of a shielded cable?
Yes. So shield termination, that really gets into our banding tools, right? So that's going to be your AS81306, right? Kick me if I'm wrong on that one. But
right.
there's a whole testing battery for that as well. There is tensile requirements for that. You're also going to be checking to make sure that you have continuity, grounding, to ensure that you've got that clear path for whatever your shielding is that you're trying to work with at that point in time.
Okay, thank you. It looks like we don't have any more questions, so I think we'll wrap up here. We want to thank our speakers and our guests for attending today's webinar. Actually, we just got another one come in, so I'll answer that before we go. Could a pinched crimp cause heat or fire issues with a high voltage wire?
Absolutely.
Yeah.
Right. So I think we had a graphic where we had some folks trying to crawl through a little pipe. That's really a good example, right? You also will hear about the garden hose analogy for working with electricity. So when you reduce that cross section, right, through a crimping process, you're reducing the effective cross-sectional area, which means you're going to increase your resistance, right? So if you've got a nominal conductor voltage, or not voltage, amperage rating, and then you pinch it off too much, then you could end up overheating and causing a fire, right? So it is very important. High voltage really is not different than our standard processes,
Mhm.
but you're kind of turning up the amplitude to 11 on
Mhm.
everything, right?
Yeah.
That definitely sounds dangerous. What are the risks for an over-crimped connection is another question we just got.
Yeah, so that heat buildup that he was just talking about, but then also when you over crimp, you can cause a poor tensile test as well. Because if you over crimp to the point where you're damaging the strands, you can actually get lower tensile value by crimping too much
Mhm.
inside there. And that's indicative of the type of failure mode you see during tensile testing, whether the wire pulled out, whether it was a wire fray break or a break at the crimp, where you can actually look down inside the separated terminal and you actually see the strands are broken like right where the crimp happened. That's an indication that you've over crimped.
Awesome. Okay, another question came in. So we answered that. So I think we're all set here. If there's no further questions, we want to thank everybody for joining again. Shortly after we wrap up, you'll receive a follow-up email with additional resources and a recording of today's session. We hope to see you at our next webinar that will be September 16th at 11 a.m. Eastern Standard Time. We'll be talking all about grip tools. So thank you guys so much, and we'll see you next time. Bye.